Hello, we are Team 9. Last week we looked into the cantilever part construction method of the three CCTV headquarters buildings considered by the contractor and why the balanced cantilever method was adopted. In addition, we learned how to perform the exact engagement of cantilevers, which was most important when applying the balanced cantilever method. This week, we will learn about the design and composition of the core according to the shape of the tilted building, and how to bend the crane and the member that played the role in transporting materials during the construction of the CCTV headquarters. The tower part of CCTV headquarters has a 6-degree tilted shape. OMA considers the tilted core structure to reflect this tilted shape in the initial design stage to maintain a consistent planar arrangement. However, the tilted core structure has some problems. First, tilted cores resulted in asymmetric load distribution, making it difficult to secure structural stability. This led to the generation of additional moments, resulting in the need for more special materials such as steel and high-strength concrete than typical vertical cores. These special materials contributed to a significant increases in the overall construction cost. Second, when the elevator's travel path was oblique, the passenger's travel time was prolonged and the elevator's operational efficiency decreased. In addition, the technical complexity of the elevator system also increased, adding difficulties to operation and maintenance. Eventually, these rising costs and technical limitations have abundance approaches using tilted core structures. What form of the core did ARUP and OMA solve the tilted form of the building with instead of the tilted core? To create a unique shape, the CCTV headquarters keeps the outer tube structure in an inclined shape, while the core is designed vertically. As a result, each floor has a different configuration, and the span from the core to the outer wall and the span from the inner pillar to the outer wall are different for each floor. Because of this design, the core of the area where the span is increasing has had to bear more and the more load. Thus, an additional column was required for the upper part, where the bottom span was greatly increased on one side of the core. The addition of the columns required a structure to support them, which was supported by a transition truss connecting the inner core to the outer tube structure. Core structures are heavily burdened because they withstand most of the forces when lateral forces, such as earthquake or winds, are at play. However, the truss acts like an outlegger to connect the outer column to the core, so that when a horizontal load is applied, the core and the outer column work together to reduce lateral displacement. This reduces the burden on the core. Transition trusses usually consist of two levels of depth, which makes it difficult to utilize the space and the floor. Therefore, CCTV headquarters mainly used machine rooms, which are spaces that are not used by most people, as outleggers. As a result, the CCTV headquarters has a vertical core instead of the tilted core. However, if one vertical core is used here, like other buildings, the tilted structure limits the space where the core can be located. The importance of the core grows further in tilted buildings, which can lead to structural instability. To address this issue, instead of placing one vertical core, we chose to place multiple vertical cores at various heights according to the degree to which the building is tilted. As a result, 7 vertical multi-core with different heights were placed in the CCTV building. In particular, the tower core, bottom core, and cantilever core were properly placed, respectively, as the core is the main factor supporting the load applied to the overhang structure. In this process, auto climbing system was used for construction workability when placing concrete on the outer wall of the core. Since the cross-section of the core is not constant, a new formwork was needed to adjust to the changes in each cross-section. Therefore, in the part where the cross-section of the core changes, a flexible climbing formwork system was applied that disassembles the formwork and reassembles it according to the cross-section. Each of these cores was designed to efficiently integrate elevators, stairs, air conditioning systems, and power and data wiring. The elevators in the CCTV building has to be located inside different core while accommodating large amounts of people, so the number of floors and users available were divided. The CCTV building has a multi-core structure that consists largely of Tower Core 1, Tower Core 2, Bottom Core 1, Bottom Core 2, and Cantilever Core, which has a total of 90 elevators arranged in this multi-core. In order to efficiently accommodate a large number of people, a number of double-deck elevators have also been arranged that allow you to board onto floors at a time. All staircases are integrated within the central core, providing safe evacuation routes in case of fire or emergency. The escape routes are designed for quick access to staircases from each floor and are used in certain areas in parallel with elevators. Temporary tower support method, lift-up prefabrication method, and balanced cantilever method were considered, and balanced cantilever method was adopted during the cantilever construction as announced in week 10. So how were the members lifted up in the process? The members used for CCTV were lifted through a tower crane. The work area was divided into 3 areas: Tower 1, Tower 2, and Podium. Tower 1 and Tower 2 were placed with one M1280D tower crane and one M600D tower crane, respectively, and Podium has two M440D tower cranes and one C7050 tower crane, which used a total of 7 tower cranes. The high-rise part of Tower 1 and Tower 2 were equipped with a large tower crane M1280D with a lifting capacity of 100 of tons, and a medium and large tower crane M600D with a capacity ranging from several tens to hundreds of tons. These cranes had the ability to safely lift heavy components even at high altitudes. Since there was a lot of work in the Podium section that required high accuracy at relatively low heights, 2 medium-sized tower cranes M440D with lifting capacity of several tens of tons were deployed. Due to the limited space in the Podium section, the C7050 crane with a wide working radius was placed at the center, and 2 medium-sized cranes M440D were placed on both sides of the Podium to efficiently utilize the space. These lifted members are joined by welding. The maximum internal force of the cantilever reached 4,975 kN, and a high-strength SIG placed fully penetrating weld connection is required to create a structure that can withstand such large forces. Welding of high-strength SIG plates typically takes a long time and requires a lot of continuous welding, which has led to the inability to weld both ends of the cantilever at the same time. As a solution to this, the two sections were quickly connected first using a temporary connection joints between the cantilevers, and then the welding was carried out. This allowed the welding to proceed while preventing damage to the welding. This week, we learned about the process of construction method of the core shapes to be determined and the combination of tower crane, arrangement, and cantilever for member delivery. At the final announcement, next week, we will announce the contents that cover the entire construction process and the systems included in the CCTV building, starting with the foundation of the CCTV building. Thanks for listening to the presentation. We were Team 9.